The next one is exercise 26. So here we are given two permutations alpha and beta in Sn, the symmetric group of degree n, and we have to prove that this permutation alpha inverse, beta inverse, alpha beta is an even permutation. That means we have to show that this is the product of an even number of two cycles. So let's see the solution. Let alpha comma beta have the following representations as products of two cycles. We know that every permutation can be written as a product of a number of two cycles, and evenness and oddness of a permutation is based on that number of two cycles in such a representation. So alpha can be written as this, as a product of some two cycles. Oh, we should not confuse this n with that n. So let me just use something else. Let me use S, and like that beta is also a product of some number of two cycles, and these two cycles are not necessarily disjoint. Okay, that is not necessary. We may have, for example, A1 may be equal to A2. That possibility is there. C2, D2, CT, DT, where S and T of course are some positive integers. Then what happens to alpha inverse, beta inverse, alpha beta? Alpha inverse, let us just first write what this thing is, and then we can manipulate the expression. A1 comma B1, A2 comma B2, AS comma BS. This is alpha inverse. Then like that beta inverse, and then alpha and then beta. Okay. Now we know how to calculate the inverse of a product of some elements in a group. That equals the product of the inverses of the elements, but the order gets the order is switched. You get the opposite order. If you calculate AB whole inverse, then that is B inverse A inverse. So like that, extending that thing, we have AS BS inverse Then if you write the one before that, bs minus 1 inverse, like that, eventually you will get a1 b1 inverse. And we can now just not write the brackets. Then like that, ct dt inverse ct minus 1 dt minus 1 inverse, like that, c1 d1 inverse. Then a1 b1 a2 b2 as bs c1 d1 c2 d2 ct dt. Now we know one more thing, that the inverse of a 2 cycle is the 2 cycle itself. So we can now use that here. as bs as minus 1 bs minus 1, like that, a1 b1. Then this is one continuous product, okay, because of lack of space we are writing like this. Otherwise you ideally you have to write it in one line. ct dt ct minus 1 dt minus 1 c1 d1. Then a1 b1 a2 b2 as bs c1 d1 c2 d2 ct dt. While carrying out this calculation, you should keep in mind that the 2 cycles are not necessarily disjoint, so they may not commute. Okay, any 2 cycle here may not commute with any other 2 cycles. So the order that is determined by this, the form of this product, you have to maintain that order. You cannot, for example, write as minus 1 comma bs minus 1 first and then follow it up with as comma bs. That may be wrong. That may not be equal to this. So you maintain the order. Okay, now notice that we have been able to express this alpha inverse, alpha beta as a product of a number of 2 cycles. Now how many 2 cycles are there in this product? We can of course calculate. So alpha inverse, beta inverse, alpha beta is a product of how many 2 cycles? We have s number of 2 cycles here in the first row. After that, here we have t number of 2 cycles. Then in the third row again s number of 2 cycles, and in the fourth row we have again t number of 2 cycles. So is a product of 2s plus 2t 2 cycles. Since 2s plus 2t, we don't really need to know what this s and t are, but this final number of the total number of 2 cycles is an even number. Since this is even. So our permutation is an even permutation. And that's just it. Use table 5.1 to compute the following. It has two parts. Part A, the centralizer of the element alpha 3, which is this product of two cycles 1, 3 times 2, 4, and B, again the centralizer of alpha 12, which is this 3 cycle. Table 5.1, if you go to the text, you will see that this table is the group table for the alternating group of degree 4. That is, those permutations and 4 symbols which are even permutations. They give us the alternating group of degree 4, A4. So this table gives us the composition table or group table of A4. Now, if you go to that table, you will see all the things are given there. If you take any two elements from A4, what their product will be, all those things are given there. The centralizer of alpha 3 will be the set of those elements by the definition of a centralizer which commute with alpha 3. So you can go to that table, and if you look for those commuting elements, you will see that the centralizer turns out to be this. Because it's cumbersome to actually write the permutations, even in the cycle form, it's cumbersome to write it. And when you are forming the group table of A4, say, what we have in this table 5.1, if you keep writing the elements like this, it will take a lot of space. So in order to save space, the author has decided to give them some names. So some such names are alpha 3, alpha 12. Alpha 3 is this thing, alpha 12 is this thing. So from table 5.1, we find that A, the centralizer of alpha 3 is this set, alpha 1, alpha 2, alpha 3 and alpha 4, and B, the centralizer of alpha 12 consists of these elements alpha 1, alpha 7 and alpha 12. Since every element in a group commutes with itself, so the element itself will belong to the centralizer. For example, we have alpha 3 here, alpha 12 here. Besides that, there may be some other things also. And of course, the identity element commutes with every element, so that will also be in the centralizer. In any case, the centralizer itself is a subgroup of the original group. Here I think alpha 1 is the identity. I am not sure. You go to table 5.1, you will know. And please verify that this is actually the case. That is, these are the centralizers. Next, exercise 28. How many elements of order 5 are in S7? Okay, the symmetric group of degree 7. We know the method for calculating the order of a permutation. If you have a permutation in any symmetric group, say you have a permutation alpha, what you first do, you express alpha as a product of disjoint cycles. Then you observe the lengths of these cycles and take the LCM of the lengths. That LCM, the least common multiple, is the order of alpha. Why that? That is so that we have already seen, we know. Now here we are considering elements of order 5 in S7. So we can start the solution like this. Let alpha belonging to S7 have order 5. Since 5 is the LCM of the lengths of the disjoint cycles whose product is alpha. Alpha itself has to be a 5 cycle. Do you see why? LCM by definition is a multiple, least common multiple. If you have a number of numbers, then LCM is the least among all the common multiples. That is, it is a number which is divisible by all those numbers of which you are calculating the LCM, and it is the least such number. Now what we have here is that 5 has to be the LCM. So if 5 has to be a multiple of something, that something can either be 1 or 5, because 5 is a prime number, and that is why the cycles that that will give us the cycle decomposition of alpha, each such cycle can have length either 1 or 5. But because we are in S7, there are only 7 symbols available and we want 5. So we should have a 5 cycle in the cycle decomposition of alpha. But if we have a 5 cycle, then 2 more symbols are there, okay, which are not appearing in that 5 cycle. Those 2 symbols cannot give you a 2 cycle, because if your alpha looks like this, say this is a 5 cycle and this is a 2 cycle, then by the method for calculating the order of a permutation like this, you will then have to take the LCM of 5 and 2, which is 10, but we want 5. So you cannot have a 2 cycle with the remaining symbols. What you can have is 2 1 cycles, and that is why, because we generally do not consider 1 cycles like that. So alpha itself must be a 5 cycle, okay, and we already know that each 5 cycle has order 5. So that means the elements in S7 which have order 5 are precisely the 5 cycles. So now the question comes down to the number of available 5 cycles, number of distinct 5 cycles in S7. Okay, and that will be has to be a 5 cycles, since every 5 cycle every 5 cycle is the order 5, the elements in S7 of order 5 are precisely the 5 cycles. The number of 5 cycles in S7 is what? Okay. Now from among 7 symbols, you can choose 5 symbols in this many ways. In old notation, this same thing, this binomial coefficient is also written like this: 7 choose 5 or 7C5. Okay, but I use this one. But simply choosing 5 symbols from among 7 symbols is not enough, because a 5 cycle is an ordered set. So the cyclic order has to be maintained. Now in a 5 cycle, since the cyclic order has to be maintained, So the elements can be arranged among themselves in 5 minus 1 factorial ways. You keep one of them fixed in order to maintain the cyclic order, and you can arrange the rest. That will give you different cyclic orders. So this times 5 minus 1 factorial, and that will be equal to what? We can in fact we can find the number. The figures involved here are not that big, so we can handle this. From the elementary properties of binomial coefficients, we know that this is equal to 7 choose 7 minus 5, that is 7 choose 2 times this is 4 factorial, and this thing is 7 times 6 divided by 2 times 24. So this means and now I have to do longhand calculation. $504. I hope the numerical calculation is correct. So this is your answer. There will be 504 number of 5 cycles, and so that many elements in S7 of order 5. Next, another similar one. 29. How many elements of order 4 are there does S6 have? And how many elements of order 2 does S6 have? Okay. Unlike the previous one, here we won't have a single type of cycle structure involved because the order is 4. So now for the order 4 we will have yes, 2 different types of permutations. One of them is a product of a 4 cycle and a 2 cycle because we are in S6, and another type is those permutations which are just 4 cycles. Okay. Any element in S6 having order 4 is a product of a 4 cycle and a disjoint two cycle, or number 2 just a 4 cycle. If suddenly this thing came to your mind, why not a product of two disjoint two cycles? That will not give you order 4, because here you will have 2 and 2, and the LCM of 2 and 2 is just 2. Okay, now we have to see how many elements there are in S6 of each type. The number, I need ink. The number of elements in S6 of type 1 is, okay, so let us first figure out how many elements are there which are a product of a 4 cycle and a disjoint 2 cycle. So they look like this. And the number of symbols we have, of course, is 6. So first of all, when you choose 4 symbols from among these 6 symbols, that can be done in 6 choose 4 number of ways, or 6C4, the same thing, but then that is just the choice. Arranging them cyclically will be, for each such choice of 4 symbols, they can be arranged in a cyclic manner in 4 minus 1 factorial ways, just like before, times the remaining 2 symbols, of course, will give you only 1 2 cycle. So times 1, because after choosing these 4 symbols we have only 2 symbols left, and these 2, we hear that is tremendous thunder. Anyway, so after choosing these 4 symbols we have 2 symbols. Now those 2 symbols will give us a single 2 cycle, and here if you change the positions, if you switch the positions of these 2 symbols, the 2 cycle does not change, so we don't get anything new here. So times 1, and this gives us what? This becomes what? 6C4 is also the same as 6C2, and that is 6 times 5 divided by 2, and this is 3 factorial, so that means 6. So we get 90. So 90 different types of elements in S6 of this form. But not just that, we also have just the 4 cycles. and 4 cycles of course can be chosen. We have already seen this just now in this many ways. So that again gives us 90. So in total we get 180 different elements in S6 with order whose orders are all equal to 4. Okay, so we can just simply write it here is, we don't write in any more detail, we will just simply write the total here, and we won't write in detail how we obtain the total. That is understood, and that is because in fact we have said okay. No, wait, I was just about to make a mistake. The number of elements of type 1 are the elements of this type, and the number of elements of type 2 are this. Okay, so we are writing separately. Okay, fine. So this is if you want to really show what is going on, you can write 2 choose 2, that will be 1. So that is equal to 90, and the number of elements in S6 of type 2 is this, which is also 90. So there are 180 elements in S6 of order 4. Next we come to the cycles of order, permutations of order 2. Next, any element in S6 of order 2 is either number 1, here also we have types of elements, a 2 cycle, every 2 cycle has order 2, or number 2, a product of, keep in mind now we are having order 2, we want the cycle or we want the permutation to have order 2. So in the cycle decomposition of the permutation, you cannot have any cycle of length more than 2, because that length will be multiplied. So you can have only cycles of length 2. So you can have a 2 cycle or a product of 2 disjoint 2 cycles, or there is another type, because we have 6 symbols, so we can also consider a product of 3 disjoint 2 cycles, where the cycles are mutually disjoint. number of elements of type 1 elements in S6, that is understood, is what? How many 2 cycles are there in S6? 2 symbols can be chosen from among 6 symbols in 6 choose 2 ways, and after choosing them, unlike the other longer cycles, in a 2 cycle, once you choose 2 symbols, there is only one order. That is because, for example, if your symbols that you have chosen are 1 and 2, then they will give you a single 2 cycle, because 1 comma 2 is the same as 2 comma 1. And if you think of it like that also, you keep one of the elements fixed and arrange the other. Arrange the other means you can arrange the other in 2 minus 1 factorial ways, that is only one way. So here the number is simply this, which is what? 15. Next, the number of elements of type 2 a product of 2 disjoint 2 cycles. First of all, for this one we will have 6 choose 2 times. Then after choosing 2, we are left with 4 available symbols, because we want the cycles to be disjoint, so those 2 symbols are gone. So now we have 4. So from among them 2 can be chosen in this way. But if you just simply calculate this, then you are actually calculating more. Do you see how? For example, say in one choice here, in choosing 2 symbols from among 6 symbols, you chose, at some instant you chose 1 and 2. For this 1 and 2, there will be this many other choices for this second 2 cycle. Say in one such choice you chose 3 and 4, but here for your choice 1 and 2, here you have got 3 and 4, but in this 6 choose 2 number of ways of choosing the first 2 cycle, there is that one case also where you can choose 3 and 4 here itself. If you do that, then here at one instant you will choose 1 and 2. There are other choices also, but this will also appear, and that will give you what? This product, whereas the first choice gives you this product, and these two are not two different things. That is because disjoint cycles commute. So that is why we are, if we just simply calculate this, we are calculating double the actual value. So we have to divide by 2. It is because the positions don't matter. They are disjoint cycles, they commute, so we won't get two different things like this. They are not different. So we are dividing by 2, and that is why here this is the number. Is 6 choose 2 times 4 choose 2 divided by 2. So this gives us what? 1/2 of 6 choose 2 we have already found. This is 15 times 4 choose 2 is 4 times 3 divided by 2. So these 2 and 4, they are gone. We have 45. And the number of elements of type 3 is, okay, now what happens here? Here something similar will happen, and we already know what will happen. Now we have a product of 3 mutually disjoint 2 cycles. So now the situation is this. So the number of ways of choosing the first cycle is this, that of choosing the second cycle. Having chosen a first cycle is this, and this one, of course, we have only one choice. We have to multiply this 3. But again, because disjoint cycles commute, so these things, whatever arrangement you choose to write them in, that will not affect the permutation. And you know that 3 symbols can be arranged in 6 ways. 3 symbols means this is one symbol, this is another, and this is another. So you have to divide by 6, which is nothing but 3 factorial. So here the number is this. Divided by 6. Times 15 times 6. 4 choose 2 is 6. Now 4 times 3 divided by 2. So here you get 15. Hence, now adding these things up, we will get the total number of elements in S6 of order 2. Thus, the number of elements in S6 of order 2 is 15, 45 and 15. $75. And let us solve one more. This is exercise 30. Prove that this 4 cycle is not a product of 3 cycles. So no matter what 3 cycles we choose, and no matter how many of them we choose, in whatever manner we want to form their product, that product will never be equal to this. That's what we have to prove. since 1, 2, 3, 4 can be written like this: 2, 3, 4. If you want, you can verify also. We have to come from that side. Recall, in calculating this product, we have to start from here. This does not change 1. This also does not change 1. This one sends 1 to 2, so 1 goes to 2. Then this does not change 2. This sends 2 to 3, and 3 is unchanged by this one, so 2 goes to 3. 3 is sent to 4 by this one, and 4 is unchanged by this one, again 4 is unchanged by this one, so 3 is sent to 4. Then this one sends 4 to 3, then that 3 is sent by this second one to 2, and that 2 is sent by this first one to 1, so 4 goes to 1. This, so our 4th cycle is an odd permutation because you have been able to write it as a product of 3 2 cycles, and that number 3 is odd. This is an odd permutation. Any 3 cycle ABC, on the other hand, is an even permutation, since just like this one you can write ABC like this: A comma B, B comma C. So it's a product of two cycles, so that number 2 is even, so this is even. Since the even cycles, or I mean the even permutations form a subgroup. Oh, we don't really need to say that much, since the product of any number of even permutations is again an even permutation So we only need the fact here that the set of all even permutations is closed. Okay, it forms a subgroup, that much we don't need. So it's an even permutation. So our odd permutation, which is this fourth cycle, is not a product of 3 cycles, because all 3 cycles are even permutations. This completes the solution. And let us just end the exercises here itself. There are more, of course, many more, but we will solve in the next Gallian update. And after this we have some ring theory exercises also. So see you in that other video.